Hello and welcome to Project 152, your weekly specialist exam prep. Now every week we go through questions from past exams from the QCAA. We're going to go through all 152 questions in this series. So we are up to week 21. It's a tech active one and it's all stats. It's a real stats week, so get ready. And we start off with a question that I think is not so easy. So we're going to go through it step by step. The mass of packages of cheese produced by a company are assumed to be normally distributed with a known mean here and a standard deviation here. Let me just draw that. So there we have a normal distribution with a mean that is unknown, but a standard deviation that is 7.37. I like to put it in here with just a little leap here because standard deviation is like our measure of spread. All right. The packages of cheese are labelled to contain 500 grams. All right, I don't know where that fits yet, so let's just write that down, 500g. Okay. It says, there is a 25% chance that the mean mass of 20 randomly selected packages will be less than the labelled amount. Okay, let me draw that. All right, so this was the normally distributed population. This is the normally distributed sample means. They're different. But they do have some similarities. The mean of the population and the mean of the sample mean are going to be equal. All right, so these are the same. We don't know either of them though. Now, it says there's a 25% probability that the mean mass of 20 randomly selected packages will be less than the labeled amount. All right, the labeled amount is 500, and it says that, 25%, so 0.25, is going to be less than 500. Okay, do I know the standard deviation? Yes, I do, as long as I remember this formula right here. So the standard deviation of my sample mean is going to be equal to the standard deviation of the population, 7.37, over the square root of the sample size, which we're told we're doing 20 randomly selected packages. So there is a standard deviation S, and it is whatever that value is there. I'm not going to bother calculating that. I'll put that in my calculator in a second. Now, we're going to draw another picture because when it comes to these unknown means, when you don't know the mean and you'd like to know the mean, often we need to go to a standard normal distribution. So let's draw a standard normal distribution. All right, so this is a standard normal, sorry I fell off the page, standard normal distribution. It has a mean of 0 and a standard deviation of 1. And I'm going to use this to calculate the z-score of 0.25. Because if I find this z-score, then I can use it in this kind of, with this stuff. Okay, we're moving in this direction. We're here now. Let's use our calculator to calculate this z-score. All right, so I'm in here. And I'm going to distributions, I'm going to normal distributions, and I'm going to go to the inverse normal. All right, so the tail is a left tail, the area is 0.25, the standard deviation is 1, the mean is 0, and that gives me a z-score of negative 0.6744. Let's write down our z-score. So now that I have a z-score, I'm pretty close. Because now I can say that the z-score is equal to the score minus the mean over the standard deviation. But we need to be a little bit careful with what we put into here. Okay, the z-score is negative 0.6744897. The score that we're interested in, the z-score is matching up with this one here. So 500. Minus, now we don't know the mean, we'd like to know the mean, over, and then the standard deviation, we're not using the population standard deviation because we're interested in the sample mean. And so we're going to use this, 7.37 over root 20. Okay, and now I have a nice little equation that I can solve. I just solve this. I might use my calculator, just say solve n. All right, I've typed all of that into my calculator with a nice little solve n at the front, executing that. Thank you very much. And the answer is 501.11. So 501.11, is there an answer there? Yes, the answer is C. Now this feels like a lot of work for question 3, multiple choice question. Is there another way that you could do it? Yeah, I can think of one way that you could do it, and that is because we know so much about our sample mean formula here, right? We can put in all 4 of these values here. Now, if we put in all 4 of these values here, how much do we have? We have everything, right? So we could say, we could do like an inverse normal with 501.11, with the standard deviation being this, with the area being 0.25. And if it spits out 500, then that's the number we're looking for. If it doesn't spit out 500, then we can just try another one. So this could have been a trial and error style question. Question 1, question 2, do all 4 of them and see which one of them works in our blue picture here. Both ways work. I've shown you what you might do if it's like a short response question. You can also do trial and error. Okay, celebrate. Next. Now, in the last question, I talked about maybe you could use trial and error. I think this is a good example of a question where using trial and error probably makes the most sense. All right, the height of all students at a school were measured. The mean height was 157. Okay, all students, so that mean is our population mean. A random sample of 35 students from the school was selected, so our sample is 35. The mean height of this sample, so sample mean, is 159.7, and the standard deviation of the sample is 8.7. Okay, and then the question says, the smallest confidence level that could be used to produce a confidence interval that contains mu, and mu is the population mean, based on this sample is. And now I'm just going to use my calculator and put in all of these confidence levels and see which of the confidence levels has the population mean inside of it. So I'm in stat mode again, and this time I'm doing intervals, and we're going to do a Z, and we're going to do a 1 sample. Okay, and now we can do all of our confidence levels. So it says the smallest confidence level that contains mu. Right, so let's try the smallest confidence level, which is 0.85. 0.85. Okay, and we know our standard deviation is 8.7. Now, a lot of people are going to get a little confused here because should I be putting in my population mean, so my sample mean, should I be dividing that by 35? This value that I'm putting in is my sample mean, and we're told that. We only need to divide by root n if we know our population mean and we're trying to come up with a population standard deviation, and we're trying to come up with a sample standard deviation. So we're using exactly what we've got because that is our sample standard deviation. What else do we have here? We have our mean, which is our sample mean, 159.7, and we have our number of samples, 35. All right, let's execute. All right, so what do we get? We get 157.5 as the lower bound of our confidence interval and 161.8. So does this confidence interval contain the population mean? Does it contain this? No, it doesn't. 157.5 is larger than 157. So if this was like on a number line, 157 would be sitting outside of it. So A is not our answer. And you can see how easy this is going to be because now we can go back to our confidence interval and say 0.9. How about that one? Execute. All right, and this time we get a lower of 157.2 and an upper of 162.1. Does that contain 157? No, it doesn't. Let's try another one. Confidence level of 0.95. Execute that. And a lower of 156.8. A lower of 156.8. Does this confidence interval, this one becomes like 162.5 now. Does this confidence interval contain 157? Yes, it's sitting right there. So our answer is, Cal, do this one. Our answer is C. Now, why did my little formula come up here? Because there is another way to do this that isn't trial and error. Now, I'm not going to go through it in full, but I'll give you the basic idea. Our lower bound is the one that we're interested in. So I can sub in a bunch of this information into my lower bound. So using that formula, this is going to be our lower bound. And we want our lower bound to contain the population mean, 157. Okay. Once you solve that for z, so z equals something, that gives you some value on a standard normal distribution, so 0 and 1. You'll get some z value, whatever that happens to be when you solve it. Once you know that, you find the area here, and the area is going to be somewhere between like that 90 and that 95. And so to figure out what confidence interval you need to use, you need to figure out like which one there is. Clearly, it's going to be a lot easier to just use trial and error on this one. That's why I'm going that way. But if you're interested, you can figure out the exact value following that kind of path. All right, celebrate, next question. So another question here where we're looking at sample means, things like that. It says the mean time for visitors spending at an art exhibition is 39 minutes and the standard deviation is 6 minutes. Now let me write that down. This is all visitors that visit this place, right? So the population mean, which we use mu for, is 39. And the standard deviation of the population, which we'll use this for, is 6. All right, so this is population information. Let's write that down. Determine the approximate probability that the mean time spent at the exhibit by a random sample of 35 visitors. So now we're doing samples. We know that n is equal to 35. We don't know what the mean is, which we'll do x with a hat on it for the mean for the sample. And we don't know what the standard deviation is yet, but we kind of do. But we'll talk about that. By a random sample of 35 visitors is between 38 and 40 minutes. So we're going to be looking at some kind of sample mean distribution. We're using a sample size of 35. Now, the mean of the sample means is always equal to the mean of the population. So 39, 39. These are different things, but they're equal. The standard deviation of the sample mean is different. The standard deviation is, have I got my formula here with me? Yes. The standard deviation of the sample mean is equal to 6 over root 35. Okay, so this is our sample mean distribution. We know that the mean of it is 39. We know that the standard deviation is this value, 6 over root 35, whatever that happens to be. Now they want to know, determine the approximate probability that the mean time spent at the exhibit by a random sample of 35 visitors is between 38 and 40 minutes. So that's what we're trying to find. Calculator. So I'm in stat mode again. I'm doing a distribution. I'm doing a normal distribution, and it's NCD because I'm trying to calculate the area. Okay, so what's my lower? My lower is between 38 and upper is 40. Now, my standard deviation, you've got to be careful here, right? Because this calculator doesn't know we're trying to do populations or samples. Our standard deviation that we need to use here is this one. So 6 over, oh, that's interesting. All right, shift square root 35. Okay, good. And then the mean is 39. Executing that, and we get a P of 0.675. Now, what's closest in our answers to 0.675? It is 0.68. Just bring that calculator up one more time. It's worth noting on this calculator that when you fill that in, if you scroll down just a little further, it will give you the option to draw it. Never a bad idea, because then you can see your picture matches their picture and everything's making a lot of sense. So a good idea to do that kind of thing. Not strictly necessary, but I think it's very, very useful. Okay, that's it. Celebrate. So continuing with the theme today, we've got another stats question. Data records show that the speed of cars at a particular location on a highway are normally distributed with a mean of 98.7 and a standard deviation of 4.1. Now this is all cars traveling through this area, so we're talking about population statistics. Alright, so I've just written that down, population statistics. It also says the speed limit is 100 kilometers an hour. I'm sure that's going to be useful information later. A police officer plans to record the speeds of 20 randomly selected cars. Alright, so we've got a sample of 20. That's important. Now let's go. Part A. Determine the expected number of cars in the sample that would be travelling within plus or minus 1 kilometre of the population mean. Okay, now this question is interesting because this question is actually not a sample distribution question. It's actually more like a question you would come up against in maths methods. Because what we're trying to come up with is the probability that any single car will be travelling within plus or minus 1 kilometre. And then from that, determine the expected number of cars that are travelling at that speed. So let's find the probability that any given car is travelling plus or minus 1 kilometre of the population mean. This is what we're trying to find out. The probability that any given car in this population is travelling between 97.7 and 99.7. That's plus or minus 1 kilometre of the population mean. Now we're just going to use our graphics calculator to solve that. And let's call it up. Now I'm in stats mode again, and we're doing a distribution. We're doing a normal distribution, and we're trying to find a probability. So it's going to be NCD. Okay, now the lower value here is 97.7. The upper value is 99.7. Now the standard deviation, 4.1. And you might be thinking, wait, don't we have to divide by n, etc., etc.? Again, this portion of the question is really maths methods, right? It's not specialist. We're not worrying about sample means yet. Okay, and then the mean is 98.7. All right, let's draw that. We can go down and draw it. All right, we get a nice little picture here, and we get a probability of 0.19269. Now, rereading the question, it says, determine the expected number of cars in the sample that will be travelling. So the expected number of cars is going to be equal to, and this is the first time when the sample comes into play. It's going to be equal to the number of cars travelling times the probability of success, the probability of them travelling plus or minus 1 kilometre. So if I type this into my calculator, I get an expected value of 3.85 cars. We would expect approximately 3.85 cars out of 20 to be travelling at that speed limit. Now, you can't expect 3.85 cars from 20. That's definitely not going to happen. So we expect about 4 cars from those 20 to be travelling within plus or minus 1 kilometre. Like I said, this is really methods work. Nothing specialist about this. The QCAA are going to do this a little bit because they want to make sure that you understand the difference between these kinds of questions. All right, let's see part B. Determine the probability that the mean speed of this sample will exceed the speed limit. All right, so look at this. Mean speed of the sample. So sample means. Now we're in specialist territory. So let's do that one. So doing part B, I'm going to use my formula here because I think it's going to be useful. Now, in terms of everything that we're doing here, we've got a sample mean. Now, the sample mean is going to be equal to the population mean, 98.7. We have a sample standard deviation, which is going to be equal to, using this formula up here, the standard deviation of the population, 4.1, divided by the square root of our sample size, 20. Okay, and then what are we being asked to calculate? Determine the probability that the mean speed of this sample will exceed the speed limit. Okay, so our sample is 98.7. Our standard deviation is this S value that we've just got here. And we're trying to find the probability that the mean is larger than 100. So now we can type this into our calculator and calculate whatever that probability is. So here I am again, and I'm going back to normals, normal distributions. I'm going NCD, and what are we going to do here? We're going to have an lower of 100. We're going to have an upper, let's just put in a really big number, 99999. Okay, the standard deviation here is going to be equal to 4.1 divided by shift the square root of 20. Okay, and then what have I got here? 98.7, same deal. Let's scroll down and we'll draw it. Okay, and we get this here. The probability that the sample mean will be larger than 100 is equal to 0.078. Let me write that in a nice, neat little mathematical notation. The probability that the random variable, that is the sample mean, will be greater than 100 is equal to 0.078. Done. That's part B. Now there is one more part here, part C. There is a 5% probability that the mean speed of this sample will exceed K. Determine the value of K. So this is a inverse normal style question. So let's do part C here. All right. And we'll just draw it. Boop. We have, remember, this is now sample means again because it's the probability that the mean speed of the sample. So we're still using that 98.7. We're still using this S value here. And it says that there is a 5% chance that the mean speed will exceed K. Right, so the area under here is 0.05. So let's find out what K is equal to using an inverse normal. All right, sorry, let's move my calculator. All right, that's marginally better. We're going to go a distribution, a normal distribution, an inverse normal distribution. Now, the tail is on this side, right? Because we're knowing that the probability is 0.05, that it's larger than K. All right, so we're not going left tail, we're going right tail. We're going an area of 0.05. The standard deviation is going to be equal to whatever this value is here. Let me just make sure that I type that in correctly. Divided by shift root 20. Yep, and then we have this 98.7. Let's scroll down. Does this draw this for us? It doesn't draw it. Okay, fine. And we get an answer of 100.207982. There is a 5% chance that the mean speed of these cars will be larger than 100.2 kilometers per hour. Now you want to get used to drawing this picture so you can represent everything, and then you can just write, using the inverse normal on the graphics calculator, K is equal to 100.2 kilometers per hour. That's nice and straightforward. Like I said, the QCAA is going to look for ways to make sure that you as a specialist student can differentiate between dealing with population means and standard deviations and dealing with sample means and standard deviations. Celebrate. So a wonderful question here. Let's read it from the bottom. Determine the possible range values that n could have been. So eventually we're going to calculate n, some sort of sample size, given that the confidence interval did not contain mu. Okay, so that's where we started. We're trying to find some sort of sample size. Let's go to the top. The mass of a certain species of kangaroo is known to be normally distributed with a mean of this and a standard deviation of this. Okay, so interesting question. We don't know the mean and we don't know the standard deviation of the population. But what do we know? When one of the kangaroos is randomly selected, the probability that its mass is greater than 83.2 is 0.45. Fantastic. I can draw this on a graph. Let's draw it. So here it is on my normal distribution. I don't know the mean, I don't know the standard deviation, but I know that the area to the right of 83.2 is 0.145. Now in situations like this, you've got to go from this normal distribution to a standard normal distribution. So let's draw a standard normal distribution. So here's my standard normal distribution with a mean of 0 and a standard deviation of 1, area of 0.145. I can find out what my z-score is by getting out my calculator. So here's my calculator, and I'm going to go distributions, normal distributions. Now I know the area, so I'm going to go an inverse normal. Now the right tail, the area is 0.145. And the standard deviation is 1 and the mean is 0. And that is my z-score. And that's very, very important. So z is equal to 1.058. So now that I have a z-score of 1.058, I think I can put together a wonderful formula, right? So I can say that z, which is 1.058, is equal to the score 83.2 minus the mean over the standard deviation. That is a formula. It's a beautiful formula. It's connecting standard deviation and mean together in one thing. Now, it's not super useful at this stage because I've got two unknowns. But if I could generate a second formula with two unknowns, I'd be in simultaneous equation territory. And I think I'm going to be able to do that if I read my next sentence. Let's just sort of move this stuff over to the side. I'm going to bring this formula down to here just to keep it safe, and we'll move on. All right, so there's my beautiful little formula. I'm going to rule this stuff off, and let's continue. We have a sample of 12 kangaroos, or when a sample of 12 kangaroos is selected, the probability that the sample mean mass is less than 74.1 kilograms is 0.079. This is another normal distribution, but with a slight difference. So let's look at those differences. So here it is. I've drawn up another normal distribution. Now, this is not the same normal distribution as this one, right? These are different graphs. This is the normal distribution as it pertains to the population, right? This is the normal distribution of the sample means, which has some key differences. Now, technically the mean here is x hat, that's the mean of the sample means, but it also happens to be that the mean of the sample means is the same as this. So even though it's not technically that, it is exactly that. All right, so these two are equal, right? Okay, what else do we have? We have a standard deviation. Now this time the standard deviation is definitely not this. The standard deviation, we'll use the letter S to denote that standard deviation, and S comes from this formula here. And we do know that we have a sample of 12 kangaroos, and we do know, or we don't know what that value is, but we'll deal with that in a second. But important to note, the standard deviation of this picture, because we're dealing with a sample, is different to the standard deviation of this picture right here. Okay, and finally, less than 74.1. So I put 74.1 here, and the area right there is 0.079. Great. We can do the same thing here and come up with a z-score using a standard normal distribution. So here it is, a standard normal distribution, mean 0, standard deviation 1, z-score 0.079. On my calculator, just need to change things up a little bit because now I'm going left tail. So let's click on our left tail right there. The area isn't 0.145 anymore, it's 0.079. And still 1, still 0. All right, and we can enter that. Now, we get z-score of negative 1.411. So let's write that down. So we've got a z-score here of negative 1.412. Hopefully you can see where this is going. I can create another one of these nice little z-score formulas. There is going to be a key difference though. So let's create our formula. We have a z-score of negative 1.412, and that's going to be equal to the score. So we did an 83.2 here, we need to do a 74.1 minus, now I said that, it's technically x bar, it's not mu, but because they're equal to each other, and because we've already got a formula in terms of mu, let's use mu here. And then we're dividing by s. We're not dividing by this here, we're dividing by s. Now, as I said, we have a formula for s right there. It's equal to sigma over root n. So we can replace s with sigma over root n. And root n here is root 12, a sample of 12. So this is an amazing formula right here because it has two variables, our mean and our standard deviation. This formula has two variables. So we've got two formulas now, two variables. We can do simultaneous equations. Let me just move this down here. We'll keep going. So now that we have two equations, we're going to solve them simultaneously. I think maybe I just need to rearrange this one a little bit and rearrange this one a little bit to get there. But we'll sort of do that as an aside. So very quickly, I'm going to rearrange that one. All right, so that's going to be equal to 1.058 sigma equals 83.2 minus mu. And that means that mu is equal to 83.2 minus 1.058 sigma. This is a good equation because we've got our mu on one side. So let's hold on to this as equation 1. So now that we've got that as equation 1, we'll do the same rearranging for this one here. Looks like it might be a little trickier. So I don't know what the best way to do this is, but maybe I'll go negative 1.412 and multiply it by this fraction. So multiply by that. So that's going to give me this over root 12. And that's going to leave me 74.1 minus mu on this side. And then I can move mu here. I get 74.1 minus all of this, but it's already negative, so it's minus a minus. So I get plus 1.412 sigma over root 12. Okay, that is my equation 2, and that one's nice as well because it's mu equals something. So let me just take that, move it up to the top. That's going to be my equation. And now I have two equations, y equals this and y equals this. Why am I saying y equals when it's mu? Because I'm thinking I'm going to graph this. If I graph this and graph this, y equals something something x, and y equals something something x, I find an intersection point. That will be the solution to my two equations. Now, hopefully I've typed all of those in correctly. I can see that I haven't because I've put the root x in the wrong place. There is a concept in computer science called garbage in, garbage out. You always want to double check when you type things into your calculator that you are typing them in correctly. All right, double, triple check. Yes, I am now happy with what I've got there. Let's draw our 2. And then maybe a zoom auto, see if that gets us to our intersection. You can see an intersection just appearing over here. Let's do a G-solve, intersection. There is my answer. Now you need to be careful. X in our equations where we typed them in was a stand-in for sigma. So that's 6.209. Let's go 6.21. And 76.63 Y. That's our answer right there. So we can type those two, or write those two down now. So it feels like we're pretty close to being done, but we haven't even read the whole question. All right, so what have I done? I know the population mean and the population standard deviation now. It's pretty much over. Let's see. A 90% approximate confidence interval for mu is calculated using a random sample of n of the kangaroos that has a sample mean of 79.1 and a sample standard deviation equal to this, which we know. Okay, good. Determine the possible range of values that n could have been given that the confidence interval did not contain the actual mean, the population mean. Okay, confidence interval. What's a confidence interval? here's a formula for our confidence interval. And what do we know? What do we know in terms of confidence interval? Well, we know this, right? Because we're told that the sample mean is 79.1. That's good. We know the z-score because we're told that we're doing a 90% confidence interval. So 1.64 is a number you should know. What else do we know? S, the sample standard deviation. Let's see. Sample standard deviation equal to the population standard deviation. So we know that as well. We just don't know root n. Now, what else do we know? What else do we know? We determine the possible range of values of n given that the confidence interval did not contain this value right here. All right, so when we create confidence intervals, we end up with two numbers, one on either side, and the idea is that we're going to find two numbers that don't contain 76.63. Now, those two numbers are going to be either side of the mean mass of the sample, 79.1, right? And we want 76.3 to be outside of this confidence interval. So the only way it's going to be outside is if it's below the lower bound. The lower bound is this first bit here. And we want 76.63 to be outside. We want it to be here. So what if I find out the sample size that puts 76.63 right here, right on the bound? And then any sample size that is smaller than that will mean that any sample size that's larger than that will decrease my confidence interval, and thus 76.63 won't be inside of it. Let's write that down as a formula. All right, here's my formula. The lower bound of the confidence interval, I want the lower bound of the confidence interval to be exactly 76.63 because that's what our population mean is. And I'm wondering what n value do I need for that? Let's go to our graphics calculator again. And no trick here, I've just typed in solve n, 76.63, blah, 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 blah. And I haven't written the letter n at the end, I've written the letter x. All right, executing that. And yes, we know that there might be more answers. Exit. We get an answer of 17.001. All right, and this is where the final trick of this question is. Because a lot of people are going to stop here and say, great, 17.001, round to 17. And the answer is not 17. No. The answer is 18. And you can check this. If you put exactly 17 in for n, and you do 79.1 minus 1.64 times 6.21 over root 17, your answer is going to be smaller than 76.63, which will mean that the population mean will be inside your confidence interval. But we're trying to determine the possible range of values of n that could have been given that the confidence interval did not contain. Something you want to keep in mind is that your confidence interval, here's my confidence interval, as n gets larger, as you have more and more and more people, kangaroos, in your sample, your confidence interval shrinks. You get more and more and more confident, right? So if we move this number from 17.001 to 17, our confidence interval expands. And if our confidence interval expands, it will now contain 76.63, which is what we don't want. So all of that is to say is, therefore, n must be greater than or equal to 18. Now, I think it goes without saying, but the QCAA does put it in their answer where n is in the set of integers. Obviously, you can't put 18.05 because it's a sample size. You can't cut a kangaroo in half. That is my final answer. That question was fun. We must have picked up our calculator like 5 or 6 times. Super awesome. Celebrate. That brings us to the end of week 21, and I think the longest Project 152 in living memory. Let me know if I over-explained these things, but I think maybe that statistics stuff can be a little bit tricky, so that's what I'm going for. I hope you found it useful. I'll see you next week for a tech-free Project 152. See ya!